I'm having to put together this problem set quickly because of the impending exams. Question 1 talks about a 0.45 kilogram ball attached to a cord and it's being rotated in a circle of radius 1.3 meter on a frictionless horizontal surface. And the cord will break when the tension exceeds 75 newtons. What is the maximum speed the ball can have? Of course, the tension in the cord is going to be the centripetal force. So it simply means that the centripetal force cannot exceed 75 newtons. The radius is given as 1.3 meter. The mass of the ball is given. And it's a direct application of the formula for centripetal force, which is mv squared by r. Make velocity the subject, force is 75 newtons, radius is 1.3, and the mass is 0.45. So the answer is 14.72 meter per second. So that's question number 1. Question 2, what is the maximum speed with which a 1050 kilogram car can turn round a turn of radius 77 meter on a flat road? So that means there is no banking in this road and it's only static friction that will keep the car on the road. The coefficient of static friction is given as 0.80. So in this case, the centripetal force should be equal to the force of friction. And the force of friction is given by mu mg, because in this particular case, because it's on a level road, if this is the road and you have the object here, you know that mg in this case is equal to Fn. And the friction is actually mu times, in this case mu s, times Fn. And Fn is equal to mg. So that's why you get that equation from which you can find the velocity. And 0.80, radius is 77 meters and g is 9.8. When you substitute all that, you get 24.56 meter per second. Is this result independent of the mass of the car? Of course it is, because in the formula for velocity you do not have the term for mass. That is why it's independent of the mass. A coin is placed 11 centimeters from the axis of a rotating turntable of variable speed. When the speed of the turntable is slowly increased, the coin remains fixed until a rate of 36 rotations per minute is reached, and then the coin slides off. What is the coefficient of static friction between the coin and the turntable? Just like in the last problem, here the centripetal force is equal to the force of friction. So when the centripetal force becomes more than the force of friction, that's when it slips away. Radius is 0.11 meter. We know that velocity is r times omega, and omega is 2 pi times f, where f is the frequency. That means it is the number of rotations in 1 second. So frequency is the number of rotations in 1 second. So we can substitute for omega, yes, and you get r times 2 pi f. Here the frequency is 36 rotations per minute, which is 36 divided by 60 rotations per second. 0.6 rotations per second. So the centripetal force again should be equal to force of friction. You're asked to find mu, so that's made the subject. And then substitute for velocity from here. Okay. On plugging in the numbers and calculating, you get 0.265 as, oh, hold on, it's 0.16. That was a calculation mistake. It's 0.16. That is the coefficient of friction. For how many revolutions per minute would a 15-meter diameter Ferris wheel need to make for the passengers to feel weightless at the topmost point? Now, when would they feel weightless? That is when the centripetal force becomes equal to the weight. So at the highest point there, the weight acts down, mg, and if the centripetal force becomes equal to the weight, that's when they feel weightless. Mass cancels out. Find the velocity. Radius is given as 7.5, g is 9.8. So you get 8.57 meter per second. But the question is asking us for the number of revolutions per minute. So from this equation, like in the last problem, we find the frequency. Now frequency is the number of revolutions in a second. So let's find that. Once you get it per second, you can multiply it by 60 to find the rotations per minute. 10.8 rotations per minute. And that's the answer. Number 5, a bucket of mass 2 kg is whirled in a vertical circle of radius 1.10 meter. At the lowest point of its motion, the tension in the rope supporting the bucket is 25 Newton. Find the speed of the bucket and how fast must the bucket move at the top of the circle so that the rope does not go slack. So there are two questions here. At the lowest point of its motion, the tension is given. So when you look at the object, at the lowest point, the forces acting are the weight acting vertically down, mg, and tension in the string, Ft. At the highest point, the weight mg and the tension Ft both are acting down. So that's the difference. Again, at the lowest point, weight is acting down. Weight always acts vertically down, and the tension is towards the center. At the highest point, weight is vertically down and the tension is towards the center. So both are in the same direction. Alright, we call the points A and B. So at A, Ft minus mg is mv squared by r because they are in opposite directions. So rearranging, v squared is this, and when you take the square root, you would get the speed. The radius is 1.10, the tension is 25, weight is 19.6, and you get 1.72 meter per second. Now at the highest point, Ft plus mg, because both are acting in the same direction, is mv squared by r. So mv2 squared by r, right? And the question says, how fast must the bucket move at the top of the circle so that the rope does not go slack. Now when you say the rope does not go slack, you're trying to say that the tension in the rope is almost zero, is reduced to zero. Because the rope goes slack when the tension is zero, right? So we set it equal to the boundary condition. Tension is zero, and therefore from that equation you can find a velocity. It's 3.28 meter per second. 6. If a curve with a radius of 88 meter is perfectly banked for a car traveling 75 kilometer per hour, what must be the coefficient of static friction for a car not to skid when traveling at 95 kilometer per hour? Now in this question, the maximum speed limit at the curve is 75 kilometers per hour, and it's banked for that. So let's find the angle of banking using that information. And then somebody's driving at 95 kilometers per hour, so he needs the extra frictional force to keep him on the road. So we can figure that out. So first let's find the angle of banking. This question has a lot of thinking. The forces that you see now are: 1, the weight acting vertically down, the normal force, of course at right angles to the surface. It's broken down into its horizontal and vertical components. So that's Fn sine theta and Fn cos theta. That's the weight mg. And in this case, Fn sine theta is equal to mv squared by r. Fn cos theta is mg. So dividing the equations, you get tan theta is v squared by rg, from which we can find the angle of banking. Excuse me. But the 65 kilometers per hour has to be changed into meter per second, which is 18 meter per second. And when you substitute that, you get the angle as 20.7 degrees. Okay. Now what you see in the diagram is the new force, that is the force of friction, and the components of the force of friction now. The pink arrows show the components of the force of friction. Friction is FFR, that is going to be FFR cos theta, and this is FFR sine theta. So when you take the forces along the y-axis, you have Fn cos theta acting up, mg and FFR sine theta both acting down. That's why both of them are negative. Okay, that's equal to 0. So rearrange that, but friction is mu Fn. So instead of friction, I've written mu Fn. And taken mg to the other side. Finally, Fn is mg by cos theta minus mu sine theta. Now considering the forces along the x-axis, you have Fn sine theta and you have FFR cos theta. Okay, you see both the forces acting in the same direction, so add them up. That should be equal to the centripetal force. Remember, it's the centripetal force that is going to keep the car on the road. So you get that, and then make Fn the subject from that. Now divide both sides, or put them equal to each other rather. Put them equal to each other, because In the two equations, you have Fn on the left hand side. So if the left hand sides are equal, then surely the right hand sides must be equal to each other. So put them equal to each other, and then some simplifications. This is just cross multiply, and distribute. You get that? Collect the terms for mu on one side. You have two terms for mu, and I've collected them on one side. And then the remaining terms, I've taken this to the other side. The masses can be cancelled. Now mu can be made the subject. I just divided throughout by cos theta. Divided throughout by cos theta. That's why the cos theta got cancelled here. Here sin theta by cos theta is tan. Same thing in the denominator, okay? And the 95 kilometers per hour has to be changed into meter per second. Substitute all those numbers now, and I know that's really small. Hope you can see it. I did try to fit it all onto one slide. Carefully plug in the numbers and calculate. And you should get the answer as 0.42. That is the answer, and this is a very good question. Number 7, calculate the acceleration due to gravity on the moon. The moon's radius is given and its mass is given. From gravitation, a straightforward question, because we know mg is equal to gmm by r squared, and the masses get cancelled, and we get the fundamental formula for acceleration due to gravity on any planet. All you got to know is the mass of the planet, or in this case the mass of the moon, and the radius of the planet. Okay. Caps G is the universal gravitational constant. .619 meter per second squared. A hypothetical planet has a mass 1.66 times that of the Earth, but the same radius. What is G near its surface? Again, from the previous formula, G of the Earth is caps G, mass of the Earth, by radius squared. And for the planet, the same thing, except that you have the mass of the planet and the radius of the planet. Divide one equation by the other, and when you divide it, you got to be careful and reverse the denominator and multiply. Just rearrange them now, and it says that the ratio of the mass of the planet to the mass of the Earth is 1.66, while the ratio of the radii is 1, because they have the same radius. So plug it into that, and you will have the answer. As 1.66 times GE. That's the acceleration of gravity on the planet. Which comes out to be 16.26 meter per second squared. And the 9th one, calculate the effective value of G at 3200 meter and 3200 kilometers above the Earth's surface. G is gm by radius squared. But in this case, the radius is radius of the Earth plus the height, as you see, because that's the total radius, right? Radius of the Earth plus the height. That's the gravitational constant. That is the mass of the earth which will be given to you. And when you add 3200 meter to the radius of the earth, which is again given, and calculate, you get 9.75 meter per second squared. So it's not much less, at 3200 meter. But when you are at 3200 kilometers, you do the same thing, but you have to change the kilometers into meters and add it to the radius of the earth. And when you do the same thing and calculate, you're going to get 4.34 meter per second squared. Because it's to be done the same way, I am not repeating it, but that's the answer you get. This time you see that the acceleration due to gravity is really small. 4 spheres, each 9.5 kilogram, are located at the corners of a square of side 0.60 meter. Calculate the magnitude and direction of the total gravitational force exerted on one sphere by the other. So you got to have the diagram, square, 4 spheres. Name them 1, 2, 3, 4. The forces that you see are the force on 3 due to 1, force due to 2, and the force due to 4. But you know that the forces due to 2 and 4 are equal. So the force on 3 due to 4 is equal to the force on 3 due to 2. And then when you use the gravitational formula, you're going to get g times the mass of the 2 divided by the radius squared, which is 250.7 times caps g. I've kept it in terms of the gravitational constant. And then to find the force on 3 due to 1, you need to find this distance, which is going to be square root of 2 times the side of the square. So get that first, and that's 0.85 meter. Then use the formula of gravitation to find the force. That is 124.91. Actually, it should be times g, okay, which I will include. And then to find the resultant of the 3 forces, what I've done is I have broken this into its components that you can see, the green dotted vectors, x-axis F31x and F31y, both will be equal, of course, because the angle is 45 degrees, and they will be 124.91 cos 45. See, because the other one will be 124.91 sin 45, but cos 45 and sin 45 are equal. That's why both are 88.32. So now take the total x component, which would be 250.7 g plus 88.32 g. And the total y will exactly be the same. $339g. Now find the resultant of the two by using the Pythagorean theorem, which is 339g whole squared plus 339g whole squared again. I've taken g out because square root of a square is just that quantity. And when I substitute all the values, I would get 3.19 times 10 to the negative 8 newtons. 11th one, at what horizontal velocity would a satellite have to be launched from the top of Mount Everest to be placed in a circular orbit around the Earth? Now, when a satellite is going around the Earth, the centripetal force is equal to the gravitational force. There you go. Gravitational force is equal to the centripetal force that you can see. And little m here is the mass of the satellite, so that cancels out. And rearrange it, you will get the velocity of orbit to be square root gm by r. Okay, the radius is given. The radius plus height will actually, radius of the earth plus height gives the radius of orbit in meters. That's the gravitational constant times the mass of the earth. Divided by the radius, and that gives you 7881 meter per second, which is 7.881 kilometers per second. Alright, now on to the last one. What is the apparent weight of a 75 kilogram astronaut 4200 kilometers from the center of the Earth's moon in a space vehicle moving at constant velocity and be accelerating toward the moon at 2.9 meter per second squared? Okay, apparent weight. See, the weight of an object is felt by the normal reaction. Like you can see the weight here and the normal reaction, mg and fn, right? The net force is equal to 0. Why? Because in the first part it's moving at constant velocity, and that means the acceleration is 0, therefore the net force is 0. So that means Fn is equal to mg, which is again g mm divided by r squared. Yeah, the little mass cancels out. You get 59.23 newtons. In the B part, it is accelerating. Therefore, the net force is equal to mass times acceleration. What happened there is I made a mistake and I corrected it. It's a little clumsy up there, but I hope you understand. So as I was saying, in the B part, it's not equal to 0 because it's accelerating. So that should be equal to mass times acceleration. Now mg is already 59.23. So all you got to do is minus 75 times 2.3 mg minus a, which gives a negative force, which means the seat belts are pulling down on the astronaut. So instead of the normal force being away from the person, it's actually in the opposite direction. That means the seat belts are pulling down on the astronaut and keeping them there. Okay, I've just cleaned it up a little bit. That is 4.2 times 10 to the 4. Okay. So now everything is clear, and hopefully you make good use of these problems and prepare for the exam. Good luck and enjoy physics.